Now we are going to discuss the probability in the probability theory. We now consider the assignment of probabilities of events. A technical complication arises here. It may not always be possible to regard all subsets of the sample space as events. So in this case, we may disregard or fail to measure some of the information and the outcome corresponding to the point omega as an element of the sample space, so that for a given subset of A of the sample space, it may not be possible to give to give a yes or a no answer to the question: is the point omega is an element of the subset A? For example, if the experiment involves tossing a coin 5 times, we may record the results of only the first 3 tosses, so that the element or the subset A is at least 4 heads will not be measurable. That is a membership of the omega as an element of the sample space A, or not sample space, the subset A, which cannot be determined from the given information about the omega. In given problem, there will be a particular class of the subset of the uh, sample space called the class of events. For the reason of mathematical consistency, we require that the event class F form a sigma field, which is the collection of the subsets of the sample space, satisfying the following 3 requirements. So these requirements, the first one is the sample space is an element of the sigma field, and all the subset of the sigma all the subset of the sample space is an element of the sigma field, which implies that the union of all the subset, okay, is an element of the sigma field. That is, the sigma field is closed under the finite or countable union. And then the third one is you have there that the sample space is an element um, of the sigma field, which implies that the the complement of the subset is an element also of the sigma field. That is, the sigma field is closed under the complementation. So notice that uh, in the given requirements, that the uh, all the subsets is an element of the sigma field. Then we could now also say, okay, since they are uh, the the all the subset is an element of the sigma field, we could now also say that the the complement, okay, the complement of those subsets, okay, so on, is an element of the sigma field. Okay, so we could now say that the union, all the union of the complement is actually an element of the sigma field. Okay, and then by De Morgan's law, we could also say that the intersection all the intersection, okay, of the subsets is equal to the complement of this one. Okay, so that's equal to, okay, you have the uh, the union, all the union, okay, of the intersection, uh, all the union of the complement. Okay, and this would be complement also. Okay, hence it also implies that this is complement. Complement. Uh, it also implies that the uh, all the intersection of the subset is also an element of the sigma field. So we could say that the sigma field is closed under the finite or countable intersection. Also, it also implies that the empty set belongs also to uh, the sigma field. Okay, so uh, for example, if the question did so let's have this one. Okay, let's write this one. If the question uh, uh, did the subset occur, okay, now if the question did the subset A sub n occur has a definite answer for n equals 1 or countable number. So do the question did at least one of the uh, subset A sub n occurs, and did all the A sub n or the subset occurs. Note also that if we apply the algebraic operation to the set of the sigma field, the new set will the new set we obtain still belongs uh, to the sigma field. In many cases, we shall be able to take the so in many cases we shall be able to take the sigma field as a collection of all subsets of the sample space, so that every subset of the sample space is an event. Problems in which the sigma field cannot be chosen in this way generally arises in uncountably infinite sample spaces. For example, if the sample space are real, we are now ready to talk about the assignment of probabilities of the events. If the subset is an element of the sigma field, the probability of A should somehow reflect the long-run relative frequency of A in a large number of independent repetitions of the experiment. Thus, the probability of A should be the number between 0 and 1, and the probability of the sample space should be 1. Now, if A and B are disjoint event, the number of occurrences of A uh, union with B in n performances of the experiment is obtained by adding the number of occurrences of A to the number of occurrences of B. Thus, we have, you have here, uh, the probability of the union of A and B is equal to the probability of A plus the probability of B if A and B are disjoint. And similarly, we have the probability of the probability of all the union of the events is equal to the sum of the probability of the subset uh, I from 1 to n if you have the subset A sub 1 or the subset 1 to subset n are disjoint. So in that case, mathematically, uh, for convenience, we require this notion that the probability of all the union of the subset is equal to the sum of the probabilities, okay, of all the subsets from 1 to infinity. When we have countably infinite family of disjoint events from a sub 1, a sub 2, and so on. The assumption of countable rather than simply finite additivity or additivity has not been convincingly justified physically or philosophically. However, it leads to a much richer mathematical theory. Okay, now a function that assigns a number of probability of A to each set A in the sigma field is called probability measure of the sigma field, provided the following conditions are satisfied. So this would be the conditions. So you have the probability of A is greater than or equal to 0 for every uh, A element of the sigma field, and then the probability of the sample space is equal to 1 if you have subset 1 to so on are this joint set in the sigma field, then the probability of the union of a sub 1, a sub 2, and so on is equal to the uh, probability of a sub 1 plus the probability of a sub 2 to so on. Okay, so okay, we may now give the underlying mathematical framework of the probability theory. So let's have the definition. The probability space is a triple. You have the sample space, the sigma field, and the probability, where uh, that's not Q. It should be uh, the big omega. So that is the space. This is a sample space. The sample space is a set. This one is a sigma field of the subset of n, and P is a probability measure of on the sigma field. Okay, so we shall not at this point embark on the general study of probability measure. However, um, we shall establish four facts from the definition. Okay, so all sets in the arguments to follow are assumed to belong to the sigma field. So let's have these general study of the four facts. Okay, so the first fact is the probability of the empty set is equal to 0. So how are we going to prove that the probability of empty set is 0? So let's have the proof. So let's have the proof. Now, we all know that uh, subset A union with empty set is equal to the set A. Hence, we could now say that the probability of A union to empty set is equal to the probability of A plus the probability of the empty set. Okay, now A and the A and the null set are disjoint. Okay, so that we could have the probability uh, so that we could have the probability of the union of A and empty set is equal to the probability of A plus the probability of the empty set. Thus, uh, we could have say that from the notion that uh, A union to empty set is equal to A. In this case, we have the probability, okay, of uh, A union to empty set is equal to the probability of A plus the probability of the empty set, which is equal to the probability of A. Okay. Consequently, we can now say here that the probability of empty set is equal to 0, since from this notion, okay, is equal to P. So it only means that this one is equal to the okay, it only means that this one is equal to uh, 0. So that's the first fact, that the probability of empty set is equal to 0. Okay, that's up the second fact. The probability of the union of A and B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. So how we are going to prove in this case? Okay, now take note as our proof. Okay, take note that A is equal to you have the intersection of A and B union, oops, okay, union to the intersection of A and the complement of B. And these sets are disjoint. Thus, the probability, we could now say that the probability of A is equal to the probability of the uh, intersection of A and B union to the probability of A intersect the complement of B. Okay. Similarly, we could have the probability of B, okay, the probability of B is equal to the probability of uh, the intersection of A and B plus the probability of complement of A union intersect B. Thus, we can now say here that the probability of A plus the probability of B is uh, minus, this is actually minus, okay, minus the probability of A union with B, and not union, intersect B. What happened to my pen? Okay, is equal to uh, probability probability of the intersection of A and B plus, okay, the probability of the intersection of A and the complement of B. The probability plus the probability of the intersection of the complement of A and B. Okay, which is equal to, okay, this is equal to the probability of A union B. Intuitively, if we add the outcomes of A to those in outcomes of B, we counted those in uh, the intersection of A and B twice. Subtracting the outcomes in the A intersect to B yields the outcome of the uh, A union with B. So that's it. We all now we now uh, prove that the probability of A union to B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. Okay, so let's have this one. If B is a subset of A, then the probability of B is less than or equal to the probability of A. In fact, the probability of A minus B is equal to the probability of A minus the probability of B. Now, take note that A minus B here is a set of points that belongs or that belong to A but not in B. Okay, so for our proof, for our proof, so let's start that the probability of okay, so the probability of A is equal to the probability of B plus the probability of A minus B. Since since um, B is a subset of A, and the result follows because the probability of A minus B is greater than or equal to 0. Intuitively, if the occurrence of B always implies that uh, the occurrence of A, so A must occur at least as often as B in the uh, given in any sequence of performances of the experiment. So, yun lang po. So, let's just write this here. There is bug in my pen, so that's why. Okay, so intuitively. Okay, okay. If the occurrence of B, okay, always uh, implies the occurrence of A. A must occur at least. A occur at least as often as B. Let's be in any sequence of the performance of the experiment. Uh, of the experiment. Okay. Okay, so let's have the fourth one. So you have the probability of the union of all the subset is less than or equal to the probability of A plus the probability of B and so on. So this one. That is the probability at least one of the finite or countable infinite collection of events will occur is less than or equal to the sum of the probabilities. Note that for the case of the two events, it follows that the probability of the union of A and B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B is less than to the probability of A plus the probability of B. Okay, so you have to take note of that. Okay, for the proof, we make use of the fact that any union may be written as the disjoint union, okay, which is as follows. So you have A sub 1 union to A sub 2 union to so on. Ah, is equal to A sub 1 union to the complement of A sub 1 intersect to A sub 2 union to the complement of the complement of A sub 1 intersect to the complement of A sub 2 uh, intersect to A sub 3 union to so on. Union 2, you have the complement of A sub 1 intersect to the complement of A sub 2, intersect to so on, intersect to the complement of n minus 1, intersect to A sub n. Okay, union to that pattern. So to see this, observe that if X belongs to the set on the right, then okay, we could now say that X is an element of the A, the complement of A sub 1, intersect to so on, intersect, okay, to A, the complement of the complement of uh, A sub n minus 1, okay, which is also intersect to A sub n for some n. Hence, we could now say that the X is an element of A sub n. Okay. Thus, X belongs to the set on the left. So conversely, if X belongs to the set on the left, then X is an element of A sub n for some n. So let n sub, in this case, let what happened to my pen? Let n sub 0 okay, let n sub 0 be the smallest such n. Okay, so we could now say that X okay, is an element so we have X is an element of A complement of A sub 1 A sub 1 intersect to so on intersect to A complement of A sub n sub 0 minus 1 because it's the smallest intersect to A sub 0 A sub n sub 0, and so x belongs to the set of the right. Thus we could now say that uh, what happened to it? So you have the probability of A sub 1 so you have the probability of A sub 1 union to A sub 2 union to so on is equal to the summation of the probability of the intersection of A, the complement of A, so on to the complement of A sub n minus 1 intersect to A sub n from 1 to infinity, which is this one is less than or equal to the summation of the probability of A sub n from 1 to infinity. So notice that the complement of A sub 1 intersect to so on intersect to the complement of A sub n minus 1 uh, intersect to A sub n is a subset of A sub n. So this basic difficulty with the classical and frequency definition of the probability is that their approach is to try somehow to prove mathematically that, for example, the probability of picking a card from the perfectly shuffled deck is one fourth, or the probability of unbiased coin coming up with heads is one half. This cannot be done. All we can say is that if a card is picked at random and then replaced, and the process is repeated over and over again, the result that the ratio of the hearts to the total number of drawings will be close to one fourth, in accord with the intuition and our physical experience. For this reason, we should assign a probability one fourth to the event of obtaining a heart, and similarly, we should assign a probability of 1 over 52 to each possible outcome of experiment. The only reason for doing this is that the consequences agreed with our experience. If we decide that some mysterious factor caused the ace of spades to be more likely than any other card, you should incorporate this factor by assigning a higher probability to the ace of spade. The mathematical development of the theory would not be affected. However, the conclusions you might draw from this assumption would be at variance with the experimental results. Um, One can never really use mathematics to prove a specific physical fact. For example, we cannot prove mathematically that there is a physical quantity called force. That we can do, what we can do is postulate a mathematical entity called force that satisfies a certain differential equation. We can build up a collection of mathematical results that, when interpreted properly, provide a reasonable description of certain physical phenomena. Reasonable until another mathematical theory is constructed that provides a better description. Similarly, in the probability theory, we are faced with situations in which our intuition or some physical experiments we have carried or suggest certain results. Intuition and experience leads us to the to an assignment of probabilities to events. As far as the mathematics is concerned, any assignment of the probabilities will do, subject to the rules of mathematical consistency. However, our hope is to develop mathematical results that, when interpreted and related to physical experience, we will help to make precise such notions as the ratio of the number of heads to the total number of observation in a very large number of independent doses of an unbiased coin is likely, or is very likely, to be very close to one half. We emphasized that the insights gained by the early workers of probability are not to be discarded, but instead cast in a more precise form. So that ends the presentation.